Okay, good evening. This is wrapping up the eighth week of the semester, and it is actually the third lecture on neural networks. We began neural networks by talking about the biological motivation for neural networks. And after that, we talked about what kind of functions are involved in implementing a neural network. These are referred to as activation functions. We spent some time discussing uh, functions such as the logistic sigmoid and ReLU and so on. And also how in feed-forward networks, these are all organized to be able to compute arbitrary functions of the input. And along the way, a whole set of parameters are needed to be learned. We simply said there are parameters, go from layer to layer to layer, and then these parameters are used in a linear fashion at every stage, and then we apply a nonlinear operator on them for the implementation. So where we're going to go from here, maybe today, and maybe I need one more lecture on that, is the network training. So how do we learn those weights for the neural network? And we can discuss this at a couple of different levels. In the first part we're going to talk about is, in order to learn those weights, you need to define some kind of a loss function or an error function or a likelihood function, which you're going to optimize, either maximize or minimize. That is how we get hold of the parameters. And so the first part, we're going to look at what are these loss functions for different problems? What are the kinds of problems neural networks solve? They can be used to solve regression problems. They can be used to solve binary classification problems. They can be used to solve multiple class classification problems. They can also be used as methods for learning generative models from which samples can be generated. So that brings in the issue of how a neural network is really learning the statistics of the data. So once you learn the statistics of the data, you can generate samples reflecting those statistics. So right now we'll stick to the discriminative part rather than the generative part. And we'll talk about the loss functions. And then how does one go about minimizing these loss functions? And how does one do it efficiently? And the efficient computation of the weights that we need to be modifying uses a famous algorithm called backpropagation. That will be the second part of the lecture that we're heading into. So the backpropagation is an interesting algorithm that uses the chain rule of calculus. So we'll spend some time on that part also. So anyway, let's begin with my first set of slides, which gives all the equations that are needed to minimize the loss function. So we'll first talk about the regression equations, then we'll talk about the binary classification equations, then we'll talk about the multi-class classification equations. Okay, so these are the things that are going to be optimized or minimized. And we'll once we fix that idea, then we go to the next part, how to implement the optimization of or minimizing these loss functions or maximizing the likelihood functions and so on. All right, so I'm going to share my screen to the first part, which is neural network training. There are a lot of equations here. I don't want you to be put off by that. And I'll just mention the highlights here as we go along. And let me put this on slideshow mode. Okay, here we are, neural network training. So this particular section has these 5 parts: neural network parameters, and all of them involve a probabilistic problem formulation. Okay, and then we specify activation and error functions. Activation, we just saw what those were, such as sigmoid. And what are the error functions, or more generally loss functions, for regression, for binary classification, for multi-class classification? And then we will state the problem of parameter optimization for those problems. And how does one solve that using local quadratic approximation and gradient optimization and gradient descent optimization. So these are several different types of approximation methods are there. Of course, you'll be primarily working with a simple method where we use first order derivatives in the gradient descent method. So once again, neural network parameters, let's see what those are. Linear models for regression classification can be simply represented by this. The output y for an input x, bold x, for a set of vector of weights w is some function f of the summation wj phi jfx. Phi jfx are the basis functions of the inputs x, and we have m basis functions, and these are the weights associated with them. Uh, in a neural network, the basis functions phi jfx also depend on parameters. And here is an example of a neural network. So we have the basis functions in these hidden network here, hidden units here, which are computed the raw inputs x1 through xd, and we get x1, this is z1 through zm over here. And those are the basis functions, and those basis functions are used to determine the outputs. In a multi-class case, there was K, capital K types of outputs. And so this output here is a linear function. All right, we have these WJs at this level or the output level. But from the input to the basis function level, those are also linear weights. So there's a recursion going on that the phi jfx in terms of consists of a summation and also a nonlinear function like f operating for them also. So that is what is shown in this equation, yk. So the kth output of the neural network involves a sigmoid here at the output levels, which is sigmoids of all of them. At the 2, the superscript 2 indicates at the second level weights. And then the inner level, that is for the hidden units, we have some function h operating on the superscript 1, which is the weights at the first level. And so this is what the output is. And if you take a look at what is the error function, and an error function, for example, in the case of regression, would be to minimize this quantity y minus tn. Tn is the target output. So for the nth input xn, the nth target tn, we take the square of the vector difference between the two, and we take the length of the vector and we take the square of that squared norm, and we sum over all the n samples that we have got multiplied by half. That is the error function. So this is the this is called the sum of squared error function. And in this slide, I try to summarize all of the different problems, the basic problems with neural networks in one slide, saying, okay, for regression, we have this f function is an identity function. There's nothing more done here. And we have the targets that we get, because we need the target to compute the loss function, which is shown over here, the targets Tn. And we assume that it's a Gaussian with mean yxw precision beta. So the y is actually the mean that is output by the network, and that is just the mean, and there is that is what is the output, and we assume that that has a normal distribution with precision beta in the variance of that. And the sum of squared errors is the regression loss function. So that is what's going on here. So the probabilistic model involves a Gaussian noise model in regression. In binary classification, F is the logistic sigmoid. It's a two-class problem. Output should be 0 or 1. And so that's or it's a probability between 0 and 1. And the distribution of the target T is Bernoulli. It is a probability of 0 and probability of 1. And the mean of that Bernoulli is given by the output of the sigmoid, sigma W transpose X. There's going to be a value between 0 and 1 with this mean here. And the yxw can be written as sigmoid with a h over here. This h function could also be a sigmoid or another activation function. And the error function here is just the maximum likelihood, or the loss function is the maximum likelihood. And we take the negative logarithm of that, and we call it as negative log likelihood, which ends up with these logarithms over here, and that has the form of cross entropy, which is a probability concept, cross entropy between the target and the output of the system. And so that's what we do in binary classification. In multi-class classification, it can consist of k binary classifications, such as is this class or not? Is this class or not? One can use F as logistic sigmoid, and the error is a maximum likelihood estimate with Bernoulli, which we just saw. In standard multi-class problem, when we say no, it is not a set of k binary classifications, but it is k values that output values that sum up to one. So we use that's called softmax. So the f function is softmax, which is a generalization of Bernoulli of sigmoid into multiclass. And the distribution now T takes on a multi-Nulli distribution, which is a generalization of the idea of Bernoulli. And again, the cross entropy function. So what does yk look like in the multi-class problem? It has got an exponential divided by summation exponential. We saw that last time. And the error function again is a cross entropy, except there's lots of subscripts here corresponding to the classes, k classes and the n samples. And the cross entropy error function, that is this cross entropy, and is the definition of the activations that are given here for this equation up here. So that slide was about all the different problems we usually solve with neural networks in the discriminative manner. All right. So we take them one at a time now, and this part of the lecture is only about equations before we go into elegant algorithms. So first is probabilistic error function for regression. And the way we come up with it is we say probability of the regression problem, right? This is just a value rather than a class label. The probability of t given x and w is defined as a normal distribution. That's what we say for regression. And we have a precision here, beta. It's a normal distribution on the output. The y is the output is a mean, and then there's a normal distribution around it. And the likelihood function is stated as a product of these over all the samples. And to taking a negative logarithm, we get the error function of that, which has got a sum of squares going on here, because the normal distribution itself has a square in its definition, which leads to sum of squares over all the samples. And there are some constant terms over here, which is minimized to learn the parameters w and beta. And the maximum likelihood approach is considered first, the Bayesian treatment considered later. Okay, so that is the probabilistic error function for regression is this. And once we somehow find the best value of W, which we're going to do by gradient descent, generally it is stated like this: WT plus 1 equals WT plus some delta times W, the delta of WT. It turns out to be a negative quantity that we want to go in the direction which is opposite to the value. There are arguments that as to why that is done. And gradient descent is discussed more fully. So anyway, this is the gradient descent part. So that's how we determine the weights W. We can also determine the beta. So how do you figure out, well, I've given you some data and you're assuming some beta here. Well, that beta can also be estimated using maximum likelihood. From the samples, it turns out that the maximum likelihood estimate of beta is beta ML is 1 over beta ML is nothing but the difference between the output of the network and the target that itself gives you 1 over the variance. That's straightforward. We're anyhow computing this, so you'll have to compute the loss function. And then, because this is the loss function, and then 1 over those is the beta. And that can also be generalized to multiple variables. So you can also figure out not only the weights, but also the value of beta. And the property useful for derivative computation is that there is a natural pairing between the error function and the output unit activation. And in linear regression with Gaussian noise, derivative of W of the contribution to the error function from a data point n, error is yn Tn minus Tn times phi n. And the output activation yn is this quantity. So the main thing to be learned there is that there is a close tie-up between the error function and the output unit activation function as well. And what else? So the corresponding sum of squares has a property that the derivative of E with respect to AK is yn minus Tk. So this is saying just taking the difference between what you're getting as output and what you should have got, that difference is the derivative of the error. So just compare the two. That is the derivative. Oh, really? That's all that is the derivative? Okay, because we are looking for the derivative, right? That's how we're going to update things. So there's a nice simple connection between all these things. And okay, that's about the regression problem. Now we have got the equations for the binary classification problem, where we're using a sigmoid for the activation. So A is the activation, A for activation. And we sigmoid it, which is 1 over 1 plus e to the power of minus A. And when you use such a model, a conditional distribution of targets given the inputs is then a Bernoulli, where you can say y of x comma w times 1 minus yx comma w1. That's the definition of Bernoulli distribution. When you have a coin you're tossing heads or tails, and I ask you what is the probability distribution in mathematical form, turns out as this form: y times 1 minus y to 1 to the power of 1 minus t. And this is the where y is the parameter, and and t is the value 0 or 1. So that is how we define that. So in the binary classification problem, the you have to follow this sequence of thinking here. Once you have the Bernoulli, you have the error function, turns out, which is actually the in this case, it's really the maximum likelihood. The negative of the likelihood, the summation over n comes about because it's a likelihood. And then we're taking logarithm, which brings in the logarithm. So it becomes the log. This is the minimizing this log likelihood function. That's where the negative sign comes into play. It's all pretty straightforward thinking that is led to this point. And then we talk about the k separate binary classification problems. This is stated in a different way, where you have k outputs. Let's say if you have 10 outputs, then a k separate binary classification problems, in which case the error function has to be stated in an appropriate way. And comparison with k class linear classification. So there are some interesting analogies between those two problems, which I'm going to leave it to you to look at. And then the standard multiclass classification. So we don't normally say that give me 10 decisions and I'll figure out how to use them. And the standard multiclass is take all of them together. And so that's where the softmax function comes into play. And again, the derivative error of the activation function is simply the difference between the output and the desired output. So this is just summarizing all of these. So for regression, for multiple independent binary classification, for multiclass classification, we have the various definitions for the probability distributions and the maximum likelihood definitions of the loss functions and so on. And okay, so for classification problems involving only two classes, we can use a single logistic sigmoid output, or alternatively, we can use a network with two outputs having a softmax output activation function. That's interesting. You can either use a simple simple logistic regression where there are no hidden units. You can bring in some hidden units to play. So if you have a two-class problem, that's an interesting question. When if you just have a two-class problem to solve, should you just use logistic regression, or should you use a neural network with some hidden units in between? The neural network with hidden units in between is trying to find a intermediate representation between the two. So it may have more power to it. So it's probably better to have a neural network if you can afford to do that. So that's an interesting issue of how do you solve a two-class classification problem using neural networks. Okay, that went pretty quickly. I didn't want to spend too much time on the equations because there's a lot to talk about on the on backprop. Okay, so let me move on to backpropagation. Okay, I hope you can see that. Backpropagation is this is, I think, section 5.3 of neural networks. So what are the topics here is we first look at what is forward propagation in a network. Go left to right, right? You apply the inputs, multiply them by the weights and get the next output, the next set of values. And then we multiply by weights and so on. All of this done by matrix multiplication. Right? The inputs are multiplied by a matrix because we've got all these cross terms going on. And so we need a matrix multiplication. So forward propagation involves that. And then loss function, we just talked about what the loss functions look like mathematically. Then we say, okay, we need to do gradient descent on these because we need to compute the derivative to update the weights. And how do you do those? Computing the derivatives using chain rule. So this is where the chain rule of calculus is used. So let's pay some attention about that. And it turns out, because these networks are complicated things, we need a systematic way of thinking about how the derivatives are computed. For that, the idea of a computational graph comes into play. And it is widely used in the deep learning area. So we first introduce it for the purpose of backpropagation. We'll talk about simple functions. What is the computational graph for a simple function? And then how do we use it for backprop? And then the backpropagation algorithm itself. And then also say if it's all about derivatives, it can also be used to compute the Jacobian matrix. And it turns out the derivatives are terribly important for all kinds of things, predictions of storms or what have you. You find that the derivative is a useful thing to compute. And it turns out the backprop is not just a tool for machine learning. It can also be used for those who are just working with derivatives of vectors and so on. And they could also benefit by using the backprop algorithm to compute the Jacobian matrix. The Jacobian matrix is nothing but a matrix of partial derivatives. Supposing I'm taking a derivative of a vector, not a scalar, a vector, and we're taking derivatives with respect to all the variables involved. So you're going to have a matrix now of all the cross terms. All right, so we'll again use this canonical neural network. We have x1 through xd as inputs. In this case, we also explicitly show an x0 as a bias a term here, which is not an input, but a quantity. And in this case, we convert this bias value to x0 as a value 1 here. And so we got this hidden layer here, which is actually the first level basis functions from the inputs. And those basis functions, we refer to them now as hidden units or hidden values. And these hidden units provide the next set of values, just like the input gave. Here, we have a new set of weights, superscripted as 2. Previously, we superscripted as 1. And they provide the outputs y1 through yk. And this is an augmented network, and these are set to be 1, in which case we are only trying to determine these weights. Okay. And of course, we want the weights over here, but it's not a bias term that's treated in a special way. Okay, now a number of weights is given by this m times d plus, okay, anyway, some calculation there. So we have d input variables, m hidden unit activate. We call them as hidden unit activations because once we multiply all of these and add them up at this node, it's got to be subjected to a sigmoid or an activation function. And so the AJ is the activation that's coming in. And the hidden unit activation functions are ZJ's HF. So some function hidden unit activation here. K output activations coming out. And these are the activations, these are the AJs and these are the AKs. And then the output activation functions YK are sigmoid of AK. So now we have the YK output is sigmoid of these, and then there is the H of these. So that is the recursion that's going on. So all of this is implemented in the form of matrix multiplication. First layer is a function of layer that each layer is a function of a layer that preceded it. First layer is given by z equal to h of w1 transpose x plus b1. Second layer is y is equal to sigmoid of w transpose x plus b with superscripts. No, the W is a matrix rather than a vector. So previously we talked about uh, W as a vector multiplying an input vector. Now we are dealing with a matrix here. For example, if we have x equal to x1, x2, x3, in this case we have three inputs, x1, x2, x3. And the weights have this W1 matrix here corresponding to this W1 up here, which consists of a transpose of the vectors W11, W12, W13 together forms this particular matrix here, and so on. So it's similarly W12 here. And so this is all shown here, what exactly is the computation. So we have, in this case, W11 times X1, W21 times, okay, so these are the actually elements here. W11, W21, W31 times X3, those are the three values that are going in here. And then W12 and so on. So we have all of these plus B1, the biases. And essentially what this network is doing is computing in matrix multiplication notation. We have a 3 by 3 matrix, W11, W12, W3. These are the elements here of this matrix. And those are multiplying the vector x1, x2, x3, and you're adding b1, b2, b3 to produce the output. So this network is just a visual representation of what's going on here, that we go from a vector multiplying by matrix to get another vector, and we multiply it by another matrix to get the output and so on, right? So this is the computation. And now let us put these ideas together before we define backprop. So we have X here as the vector input, and W is all the set of weights that are involved, the matrices at each level. And we are somehow processing these together, X and these weights W. And they go onwards to be able to compute a loss function E over, and of course, over a set of n samples. For each one sample, it will be just one value here. And that loss function EI involves what is the function that's coming out of this? And how does it differ from what it should be in the supervised learning problem? That's the loss value here. And to that loss value, we also add an additional term R for regularization. And that regularization is just a function of the W. Remember, the norm penalty is just a length of the weight vectors we are getting here. And that is simply added on to this loss function to produce the output. We can refer to this process as forward propagation. And so that is, now the regularization is what is used for the purpose of the backward propagation. So it is used for the loss function, and we don't necessarily use regularizer for the plain output y of the function. So this is for the backward part. And the loss now is EI plus R. So what is the loss? And what is the loss? Is the error, and then what is the value of the regularization? And it is the gradient of this quantity is what needs to be fed back to update the W, and then of course redo all of this to send it through to see, are we doing better on the overall loss function which we're trying to minimize. So gradient descent again, the goal is to determine the weights W from a labeled set of training samples. And the learning procedure has two stages. Evaluate the derivatives of a loss shown here. This is the nabla symbol, nabla EW, with respect to the weights W1 through WT. And use derivative vector to compute adjustments to weight. So we say WT plus 1 equal to WT minus eta, derivative of EW. What is this derivative EW? It's a vector. It's a vector of this loss function. You see this E is a loss function. It's a function of the weights, W1 and W2, the weights. And so when you change the weights, the error changes. Our goal is to somehow move from a point on this surface, which is referred to as a manifold here, and from this loss, and then we try to go to a point. It is a minimum. This is perhaps the global minimum of this function. Overall, that's the lowest value. There is another minimum here, which is a local minimum, and the goal is to go to a minimum. In neural networks, we don't worry too much about global or local minimum. In deep learning, we say, okay, head towards whatever minimum you can get. And so this is the task, to go from some point over here to a point over here. And that is done by computing the derivative at that point. It's a numerical value. So at that point, we say, what does the derivative look like? I mean, that is a numerical value, that point. It specifies the values of W1 and W2, the corresponding value of the loss over here. And we are saying, okay, not only do you know the loss at that point, can you also tell me what the derivative is? For that, we need to compute the derivative in each of these directions. And that is what's going to be used here. So let us now learn about derivatives of functions, derivative composite functions. Supposing we had only one input weight. We saw an example where we had two weights in that graph, and then we have a network with several weights in it. What if we had only one input weight? So that we understand how this derivative computation is going to work. We are using that input weight and producing an output O, right? So let's say that this was a strange network. It's a feed-forward network. It is not exactly the kind of neural network we saw. Supposing we just take that value, input weight, and we compute a function of that. Well, after all, we do that kind of thing, right? We do sigmoid of W transpose X. So let's say some function of this W. Remember, the important things in this gradient descent are no longer the values of the X's that are input. We are trying to fix the weights W's. That's what we're trying to learn. X is something that you have given me as a sample, and I need to keep it like that. And then I need to work with the W's so that I can do a good job with that X that you have given me. So this is all about W's. So we're computing f of W. Let's call the f of W as y, because we need to do this again. So it's kind of awkward to carry along f of W. We'll call it as y over here along this path. So we take that y and we compute some g of that y. Similarly, we're calling the same fw as z here or z here. And then we are computing a function h of that thing. Okay, this network is doing that. So this is just computing a y out of it. And then one more time, we are computing a function. Remember, the kinds of functions we do with neural networks are called composite functions. Function of functions of function. So this is f is a function of w. G is a function of f, all right? Similarly, h is a function of f. There are two different functions here. And then again, we use this p as an argument. P is the same as gy. And then this q is same as hz. And we compute one more function k, which is a function of these two arguments you gave me, p and q. That's the output. Okay, that's interesting. And we now say our goal, we have some loss functions that has been defined, which is available to us. And in order for us to minimize the value of the output with respect to the loss function, we need to somehow compute the derivatives. What kind of derivative would you like? We say, well, we need a derivative of the output with respect to the input. How should I change this W so this O is as good as possible? All right, so we need the derivative, partial derivative. Let's call it the dou O by dou W. All right, so that's what we want. We want the derivative. Along the way, there's so many things happening, but that's the derivative we want. And once we get the derivative of that, we're going to go and update the W using that. So this graph here says that there are some pathways here. So what we have is this O is a composite function. It's a K of PQ is O. And what does that mean? K of, what is P? P is nothing but G of FW, G of FW. And the other one is H of FW, right? So this is a, G is a function of F, H is a function of F, K is a function of both G and F. So we call G as a composite function, H as a composite function, K is also a composite function. So it's functions of functions. When you have composite functions, you can compute the derivatives as partial derivatives using the chain rule of calculus. So it says derivative of O with respect to W, which is what you're interested in, can be written as O with respect to P, which is this term here, and then P with respect to Y. All right, and then we have, because P is a function of Y, and then Y with respect to W. So we can trace back here O with respect to P, and then P with respect to Y, and Y with respect to W. All right, so this is the backward. So it's a product. It says, okay, so I need some derivatives local. We need a derivative here, we need a derivative here, and we need a derivative here. So we just multiply all of these derivatives to give one term. It's got two terms here. P has this part along this path, and then this one also, the output has got another path here. We say we add the two paths. Of it involves a derivative with respect to this W. So that is simply an addition of that. So this computational, we'll actually see a specific function of that form. So we say the derivative of O with respect to W can be written as the derivative of K PQ with respect to P, argument P, and we have another term K PQ with respect to Q. There are two of them. And in the first one, first path, we have a G prime of Y, this is the derivative here, and then F prime of W. So we need the derivative of this function, derivative of this function. And we are taking the derivative of this output with respect to this K function, all right? Derivative of K is that same quantity with respect to P, okay? So we say there are two pathways here. The derivative is computed in this pathway and the other pathway. Let's see one more example here. In this example, let us now not worry about neural networks and how they're working with weights. We're going to be using it only for weights. Supposing we had a function E of A, B, C, D, E for a energy or loss function, okay, same kind of function we had before. We will draw this graph called a computational graph of what's going on. We will say that the output E, I'm using lowercase e here, is A times B plus C times log D. Supposing this was what this network is computing. The output is coming out here. There's some network that is behind it. And again, these are all like, we can say this E is a composite function because it's a function of AB and as well, it's got two arguments. It is a function of C log D together, right? So, but we can say that AB itself can be thought of as a composite function of A and B. And this C log D is a composite function of C and D, right? So that composite functions can be written as E equal to U plus V, where what is U and V? U is nothing but AB and V is nothing but CT. What is this T? T is equal to a log D. Okay, so we say, and we draw that graph here. E is computed from U and V. U is comprised of A times B, and V is comprised of T times or C times and T turns out to be log of D. Okay, so this is the computation. Well, let us see how we can apply this chain rule of calculus to systematically compute the derivative of this E with respect to all the inputs, we want the derivative with respect to A, derivative with respect to B, whereas derivative with respect to C, and derivative with respect to D. Well, the calculus of computing derivatives, we can just look at this expression and say, that's not a big deal. I can tell you right away. What is the derivative of E with respect to A? Well, okay, it's all partial derivatives. So one variable, we're taking a derivative of, the others are all assumed to be constant. So those derivatives go to zero. So derivative of E with respect to A is nothing but B. It's B times A, right? Derivative of E with respect to A is nothing but, B is nothing but A, right? That's what this second one is. Derivative of E with respect to C is, oh, it's C times log D, so it's just log D. This is from basic calculus. And then derivative of E with respect to D, oh, D is log. So we know that derivative of log D is 1 over D, right? Right. Um, and then it's multiplied by C, that is dE by. So these four comes from calculus. And this says, well, if you want to calculate, yeah, that is based on our knowledge of calculus, but it's going to be done by this algorithm here. And this algorithm is based on chain rule of calculus. It says E, okay, in between the two is derivative of E with respect to U. In between of these two is derivative of U with respect to A. And so we are going to use chain rule that's going to say derivative of E with respect to A is the product of derivative of E with respect to U times derivative of U with respect to A here. And then similarly, we have two terms here. It's got to take this term also into account to calculate. Oh, this one is with respect to B. So we can calculate derivative of E with respect to B. And similarly, there is this pathway, and then there is also adding of these terms here. And another thing we want to keep in mind is what are these network? This is a computational graph. It is a sequence of steps involved in performing the computation. Actually, in deep learning, for backpropagation, they explicitly compute a graph like this. Here is a network that you got, but you're going to be figuring out how to update the weights. And then for that, you create this computational graph of that and use that graph to determine all the derivatives that you can now add them on. So we are looking for a derivative of, in this case, derivative of this E function here with respect to A, B, C, D. We're looking for a Jacobian here, derivative of E with respect to W1, W2, W3. That's the kind of thing we said the derivative is all about. In this case, this is the network we have. This is the kind of function it is computing. And we said, tell me what is the value of the derivative at A equal to 2, B equal to 3, C equal to 5, D equal to 10. Let's say those are the parameters at the initialization stage, right? So we know the value of A, we know the value of B, we know the value of C, we know the value of D, and I need the derivative. Okay, so it says the derivative of E with respect to A is simply the product of these two guys here, 1 and 3, and that's equal to 3. Derivative of E with respect to B is the product along this pathway, that is 1 times 2 is equal to 2. Derivative of E with respect to V is 1. I mean, we know these derivatives because they're trivial, because E with respect to U, because we know these functions, E, U, V, right? We know the expressions, so we can evaluate them. And we know that derivative of E with respect to, because those are the answers. So derivative of E with respect to U is equal to 1 because of the fact we are taking derivative of this expression. Derivative E with respect to U is 1 because V is constant, right? That's why it's 1. Derivative of E with respect to V is also 1. Derivative of V with respect to V with respect to T is exactly equal to C. So these boxes here are all predetermined expressions because we know the relationship between the input-output variables. We can evaluate those derivatives along the way. So we just need to plug in the value. If say, okay, you're saying dv by dt is equal to c, what's the value of c? You're giving me c equal to 5, plug that in, that's 5. So this becomes 1 times 5, uh, and then we, with respect to d, there's one more variable d here, right? So 1 times 5 times 0.1 says derivative of e with respect to t is 0.5. All right. So like that, we get derivative of e with respect to c also as 1. Okay, we got all the derivatives, 3, 2, 0.5, or 3, 2, 1, and 0.5, which is what this vector is. So you see, the process here of chain rule and back propagation, you're computing all the derivatives and passing the values backwards, is able to compute the value of the derivative vector, which is called the Jacobian. So this is the value of the Jacobian we have computed. All right. Oh, I've got a few more examples here. You can just play around with this. It doesn't tell you that much more. It's just for practice kind of thing. F of x, y, z is equal to, supposing there's this function. It's not a neural network, but look at this function. It's going like this: x, y, z, and it's x plus y here and x plus y times z over here. That's the network. And we are saying, okay, supposing x, y, z have values minus 2, 5, and minus 4. Tell me what is the value of the derivative of f with respect to x, with respect to y, with respect to that's the partial derivative with respect to each of these. So I need to calculate 3 derivative values. So how do I do that? Is the same kind of process. We think of q as x plus y and f is equal to q times z. So we can talk about dq by dx and dq by dy, and we can talk about df by dq and df by dz. And those are all the expressions here. And if you want these df by dx, that's what we want. So df by dx and df by dy and df by dz. We start by looking at the output over here. We need the derivative of df by df is being used here is the output here. And then we have to multiply along the way. I think the next slides illustrate that point. So first you take df by df is equal to 1, and then you have the values being computed along. There's just one step over here, and that becomes equal to 3 for this quantity, because it's directly with respect to z, and you do the other ones following chain rule. Anyway, it's kind of a little laborious, but I saw this example, which might be a nice one to have to try out for yourself how you calculate the derivatives using a computational graph going backwards, and locally you got all the derivatives. You just multiply all of them to get the final values. And so you get them as minus 4, and 3 is the value of the derivative. One more example, which kind of says, well, what about a simple neuron? Which takes as 2 inputs x and y and output z. These x and y would correspond to weight. These are not like a neuron with values x's. We are thinking about the weights only here, and there is an output coming out. So you can calculate. We also need to know the derivative of f with respect to, which is maybe the sigmoid function with respect to w, and those can be used. And you're using chain rule of calculus, and based on the output loss function you have defined, you can now propagate of the loss function with respect to the weight over here, with respect to the weight over here, using simple loss functions. All right. So anyway, that is the main concept behind the back propagation. And you see a lot of blogs, and people have written trying to explain to each other. I need to learn about computational graphs. I need to learn about backprop, and for any arbitrary function, so on. Like here, they're taking something here. Supposing f of x equal to e to the power of sine x squared. Now we are just into the domain of calculus, saying, can I use computational graphs to compute the derivative of this quantity? And it says, well, you draw a computational graph here, functions of functions, that kind of thing. So we say that the function here is of the form f of x equal to e to the power of x. That's the output. The output is f of x e to the power of something. And then there, in turn, we get a x squared as a function, as a function of x, and then we have sine of x squared as a function. So we got a function of x over here, and this is another function of that function, and the function of that function. So we have f of u equal to u of gv and b of hx, and it is x squared. So this is something like a forward propagation type of algorithm, and we have this function, and one could use backprop to do these kinds of tricky things. And it's hard for me to lecture over this too much. But as you can see here, you've got the chain rule of calculus playing a role. And for between each nodes, because you know what the function is like, you would know what the derivatives look like. Derivative of sine is cos, derivative of x squared is 2x, derivative of e to the power of something is e to the power of something, that kind of a thing, right? So you have to plug all of these things in, and then it goes on doing that. And so you are able to figure out the derivatives at the inputs of the output. So what it's saying is, how much should I change the weight so that my output is going to do well? Okay, so that's what's going on here. So anyway, the backprop is about evaluating the gradient. It's an efficient technique for evaluating the gradient, and more of this terminology and usage, and give some details over here about the calculus, specifically applying it to the loss function of neural networks. Now that we know the basic idea of chain rule of calculus and how we simply multiplying backwards, it's not complicated, but it's all being specialized here. What if the loss function was the sum of squared errors? What does the derivative look like? Instead of the arbitrary functions, we are now talking about the derivative of this error function. You see the 2 has gone, this 2 is cancelled off with this 2, and then you got an x coming into play here. And so that is what all these things look like. And then it shows all the update rules and the like, and so on. So nitty gritty detail of all of that here, and chain rule. And then it's all being stated here in a simple way: error backpropagation algorithm. Apply input vector x into network and forward propagate through the network. And then evaluate delta k for all output units, delta k equal to yk minus tk. You see the derivative at some point becomes just a difference here because of the square term and all that. And backpropagate the deltas using an exponent, summing over all the pathways, and then there is a derivative of the activation here, and that is the term to update the derivative. This is the term, and then of course we got to use it over all the values, the k values that are involved here. And that is being applied with the tan h is equal to this, and tan h, this is the activation function, and it has a simple form of the derivative that's being used, and so on. So there's a lot of detail over here that you can take a look at, and what the derivative vector looks like. This is the derivative vector which is going to be added on. And I also have a numerical example here of the kind of thing we just saw, except we saw a tree structure. This time we have x1, x2, x3 going into 4 and 5 and 6, and it gives you all the nitty-gritty details of when the values were given. Then you want to figure out the value of the derivative. Okay, so these things are all the variables in the network, I think, D, M, K, and N. And it shows you what the weights are going to be in this particular network, what values they take, weight update values. So it shows you the intermediate steps on the and these deltas here, and the input. They started with a certain initial input and weight values. These were the inputs, 101, and then the initial input. This is the starting set of weights over here, and then they apply some samples to it, and then which creates these weight updates and so on. It shows you the exact calculation. And all of that, I know in the olden days, we used to run this course with MATLAB instead of Python and Keras and so on. So I got some MATLAB code for doing all of this. And there's another point here is that the efficiency of backprop. This is a uh, order W squared for numerical differentiation with a number of operations to compute derivatives of error function, scales with total number W of weights. Single evaluation of error function on single requires order W operations, in contrast to order W squared with numerical differentiation. So backprop is efficient compared to a naive approach to computing derivatives. Squared would be impossible, right? With millions of weights, so on. So the summary of backprop is the derivative of error function with respect to weights are obtained by propagating errors backward. It's more efficient than numerical differentiation. It can also be used for other numerical computations such as Jacobians. The Jacobian matrix over here, where you have a set of outputs y1 through ym, and then you have derivative inputs x1 through xn. So I've a vector x coming in and a vector y going out, and I want all the derivatives of the output with respect to all the inputs. So this is computing a whole bunch of derivatives to see how the function is changing. And the Jacobian matrix can be computed using the same ideas. And these Jacobian matrices are used, this is kind of going away, but it's simply telling you Jacobian matrices are useful in systems design where they are computing how the malfunction of some input, how does it affect the overall output? So you're asking such questions. So we have all these subsystems. So how you multiply all the derivatives to figure out what change. Supposing this changes a little bit, how much does it change will it cause out here? So that can be used to see the sensitivity. You want to check the sensitivity of this box. If I change a little bit, how much will the output change? So you want to study that, well, derivatives and Jacobians become useful, right? Okay, so that's all I got to say about backprop and network training as such. And then we move on to other topics with neural networks, such as regularization and optimization a little later. Okay, so I'm going to stop here and I will stop the recording.